Previously, I had I'd set up some code to estimate the present value of a bond with a discrete discount rate. And in this video, I'm going to just take that a little bit further and estimate the yield to maturity in a bond. So an example we could have a look at here is based on this motivation here. So we could say, what if we knew the cash flows associated with a particular bond? So let's say we have a coupon of 60 for 1 year, 2 years, 3 years, and we have a face value of 1,000, and we know that the market price of the bond is 1,010.77, and we wanted to estimate the discount rate, R, which is fixed over the 3 time periods, the discount rate consistent with a market price for the bond of 1,010. Now previously we had set out some code in Visual Basic to estimate the the yield to maturity of a bond, and I had set it out as, well, in this case it's 2 functions, and here we had an implementation of a bisection function. I want to do the equivalent in C++. So I have some code, and we might have a look at code first and then copy and set up in Xcode. So this is really an implementation of yield to maturity using C++. And so the code is broken up into a couple of parts, but we could make this just a little bit bigger to get some sense of what's going on. So we include in these libraries in Outstream and CMAT that has functions for power and so on. And then we first of all have a function. So if you like, there are 2 main sections here. The first set of commands are designed to basically estimate the value of a bond. So if you like, we have a loop type structure. So we have the face value of the bond, we have the coupon rate, we have the discount rate, we have the frequency of the coupon payment. Is it once a year, twice a year? Does it have higher frequency coupon payments per annum? And then the time period in terms of the maturity, expressed in this instance the number of years. And then we initialize the bond as having a value of 0. And then we say the total number of coupons is equal to the time period by the frequency of the coupon. And then the coupon, the cash coupon, CPN here, is the coupon rate divided by the frequency of the coupon payment times the face or the principal of the bond. And then we set out a loop, and if you like to see this in terms of, so basically we're saying, okay, we're going to loop the coupon. The coupon is happening once, twice, 3 times, but of course it could go on longer. In this case it's just for 3 years. We want to discount the coupon at 1 plus the rate of interest, or the discount rate, times to the power of the year. And again, the same thing again, to the power of the year, and the same discounting as well on the final coupon. And we'll separate the 1,000 in the code in a second. So we have, if you like, we initialize this bond process here by saying, okay, well, BV is 0, and then we add on the coupon, and this is the function for the power, and I is the time scale. So we have 1 plus the rate of interest in where the frequency is once a year, then this just becomes 1, so no effect, so it just collapses to 1 plus R, and that would be the time period involved. And again, if M was equal to 1, I would represent 1 year, 2 years, 3 years. So once we've discounted coupons, we then move on to taking the present value of the coupons, putting into a bucket, and then adding on, if you like, the discounted face value of the bond for the maturity involved, and then we return BV. So this BV represents a bucket that incorporates the discounted coupons and the discounted face. So that function is there. But what we're looking to estimate is really not the present value of the bond, but we're asking the question, we know the present value of the bond, we know the bond price, because that market price can be observed in the market. What we're looking for is how to estimate the yield to maturity of the bond, the discount rate consistent with this bond price. Given that we know the coupons and the face, what rate of interest or discount rate is consistent with a bond price of 1,010.77. Okay, so let's take that bit of code and just take a look at the next section. Well, the next section maybe we can bring down is the bisection. Okay, so we want to look at the bisection, and what the bisection is putting in place is saying, okay, let's take the yield to maturity function. Let's set out a command, give it a name, bisection yield to maturity. Let's take the face, the coupon rate, the target. Now the target here just represents the 1,010.77. It's the market price of the bond, so the present value of the bond or the market price observed today. So if you like, it is a target, and T is the maturity, M is the frequency of the coupons, and A and B are the initial guesses for the discount rate. So we know the face, we know the coupon rate, we know the market price of the bond, we know the maturity, the frequency of the coupon, and we're going to initialize a guess on the interest rate or discount rate by taking a lower rate, A, and a higher rate, B. And then we set out, okay, we want a maximum number of iterations. We're going to say don't go more than 50,000 iterations. Then there's a tolerance level that we're specifying as being very, very low. So 0.000, etc. 1. And the midpoint here that we're setting out is equal to, if you like, an average of A plus split B, so divided by 2. So we'll see how that becomes relevant in a moment. But the midpoint is an average, and that averaging becomes useful as we progress the estimation. And then we look at the, again, we're saying that mid CDF, we're declaring it as double also. And we can see down here that that's equal to the difference between the market price of the bond and then the present value, where we're using the face, the coupon rate, the average of A and B, the frequency, and the maturity. Okay, so we set out this estimation. Our starting point here would be multiply, we run two estimations for the value of the bond, one with a low rate of interest, a low initial guess, and B with a higher initial guess. So that becomes the low difference. So if you like, we have the target value is the actual market price of the bond, and then we run an initial guess as to what the discount rate would be, and we have a low initial guess and a high initial guess for A. So these are discount rates that we plug into our PVB formula that we call up from the previous code up here, and it runs an estimation to get the present value of the bond. If both figures are positive or both figures are negative, then our initial guesses are outside the range and we should return a value of -1. In other words, we should either make A lower or make B higher, or do both until we reach a point where the return is no longer -1. So if we put in very narrowly, if we put in a range of values that are very close to each other, chances are we might get a -1. If we widen the net out to get a very low level of A and a very high level of B, then chances are we won't have a negative coming out. Okay, then to get the bisection going, we set up a loop and we say run this estimation until that in such a way that we don't exceed the maximum iterations, and we put in an initial guess for A and B. So if you like, down here when we set out the main part of the function, the parameter values that we enter in for A and B are less than 1 basis point, and 10 here would represent 1000%. 1 would be 100%. So these are expressed in decimals. Okay, so if we put in a value of A less than virtually 0 and B 1000%, we should capture all scenarios. So it's a wide enough range. But if B was a very high value, it would push up the midpoint. So if A was virtually 0 and B was 100%, then half of that would be, or if B was 1000%, half would be 500%. So we would get virtually a value here of, if we estimate with a discount rate of 500%, the present value of the bond would be very, very low. So if the absolute value here, the difference between the market price and the present value here, which is the calling up the loop function we had before, if we have a very high rate of interest, then the difference between the target value and the PVB will probably be very high. And if the absolute value of this is not less than the total, or if it is less than the tolerance, then we should go straight to just returning the average of those two values as the midpoint. But otherwise, else, if this value is greater than 0, which is going to happen if A and B combined together divided by 2 is very, very large, this would be small. This would be their market price of 1077 or whatever, and the difference would be positive. So if that were the case, then B should drop back to the midpoint. In that instance, the new B should go down to 500, and that would go back into A and B again, and the average of those two of 0 plus 500 would be 250. When you put 250% interest rate in here, still very high rate of interest, push down the present value of the bond very low, target value too high, and we'd keep going through the loop. Okay, so let's just copy some of this code here and set it up in Xcode. So I'm just going to copy the code that we have, edit, copy, and go into Xcode. So I'm going to escape, go into Xcode, so set up, create a new function, and I'll put next present. Okay, so we'll call this YTM bond discrete. Next, and create. I'll complete this in the next video clip.